Welcome, this is lecture number 49. In this lecture, we are going to talk about the linking. We are going to link switching boundary and PID controller structure in switch mode power converter. So, the concept cover here, we are talking about traditional PID controller in DC-DC converter and their limitation. Then we want to show alternative PID controller form in DC-DC converter, and then how can you link PID controller to switching surface in switch mode power converter, and what are the tuning objective and link with the performance optimization that we need to identify. So, first we want to revisit our PID controller, which we have already discussed in the previous lecture during the small signal design. In lecture number 34, we have discussed about PID controller tuning in a buck converter using small signal model. So, if we take an ideal PID controller, we generally take a proportional controller gain. It comes with a proportional controller gain. So, this is our proportional controller, this part is the integral controller and this is a derivative controller, right. But you can write in the compact form in this way. But the problem is that means an ideal PID controller has 2 0 and 1 pole, which is physically not realizable, because this is an improper transfer function, In fact, an ideal derivative, it cannot be realized. That means it cannot be realized because of finite bandwidth in an op-amp, right. So, it cannot be realized. That means we have to think some practical solution, and we have already discussed a practical PID controller. What we do, we add a derivative filter, which is nothing but this. So, that means our ideal was Kd into S, that was our ideal component. We keep the same thing and we change it to Kd into S by S tau d plus 1. So, this tau d time constant choice is very critical, because if we take the time constant to be very large, then it will not behave like a derivative action. That means, we need to choose the tau d small, so that we closely resemble like an actual derivative, but of course, it will put a limit in the bandwidth, because generally this comes from the op-amp bandwidth, but whenever you are talking about, let us say 1 megahertz converter, we take some hundreds of megahertz op-amp as an error amplifier. So, as a result, the op-amp bandwidth is pretty large, but sometimes we may not even want such a high bandwidth for the derivative filter, because we need to attenuate certain switching noise. So, in that case, we may want to increase the tau d slightly. So, generally tau d is taking like a TSW by 10 or TSW by 20, something like that, nearly like that. So, it is generally taken this is less than this, okay. But it is again the designer choice whether it is possible to implement it or not, okay. So, we need to be careful about the choice of this tau d. It is generally much smaller than TSW, should be. So, that means a high frequency pole 1 by tau d, because we can write S tau d plus 1 in this structure like a S by 1 high frequency pole plus 1. So, here this high frequency pole is nothing but 1 by tau d, okay. And this high frequency pole, due to the bandwidth limit of the op-amp, as well as sometimes we need to deliberately add that increase this time constant or decrease the high frequency bandwidth, so that we can attenuate the noise. So, that means we know about this PID controller and we know how to write it down, and that we have discussed in detail in lecture number 34. Now, the structure of the PID controller, either you can take a parallel PID controller or you can take a series PID controller in this form, and it can be framed into this problem, this series controller. That means, this is a PI counter part and this is a PD counterpart. So, this can be combined to create a PID controller. So, the PID controller is very useful because we know if we increase the proportional gain, the overshoot increases. It has minimum response, a minimal response in the impact in that settling time, but it reduces the steady state error as the proportional gain increases. Now, increasing Ki has a drastic effect on the settling time, and it try to reduce the steady state error, and it also increases the percentage overshoot, but the derivative action try to help because it introduces damping. So, it try to reduces overshoot undershoot or also reduces settling time because it try to damp out. But if you take a PID controller in a DC-DC converter, the derivative part of the PID controller create a trouble. Suppose if you take a buck converter and if you draw the waveform of the buck converter, that means if we draw the, let us say, so we are drawing the voltage and the current waveform. So, suppose we are drawing the inductor current waveform like this, and if we extend this. So, because then since there is an ESR, first consider the effect due to ESR. If there is an ESR, so suppose we are talking about RC to be not equal to 0, but LC equal to 0. ESL, we call this as an ESL, effective series inductance. If we take that to be 0, then how does the ripple look like? So, this is my voltage. So, it will look something similar to the current profile, because this will be dominated if this is M1. So, this slope will be M1 into RC. That means, if your capacitor is large and if you have some amount of ESR, then the ripple, the pure capacitor ripple will be small. So, it will be primarily dominated by the ESR ripple. Now, in presence of ESL, what will happen? Suppose this ESL. So, this ESL is very small, even it can be few nanohenry or even hundreds of picohenry. So, if suppose if you take the derivative of the output voltage, that means it will be RC, because what is the output voltage equation? Output voltage equation here, RC into IC plus Vc, which is nothing but this voltage is Vc, the capacitor voltage plus LC into DIC dt, because that is the voltage across this particular part. So, this branch voltage is here. Now, if you take the derivative of the output voltage, this is exactly what we are talking about, the derivative. What we will notice that this term, because IC, so it will create like, that means if you take the derivative, so this is my current, that means if you take the capacitor current, so if you remove the average current, it will be the capacitor current. So, capacitor current will be similar to the triangular wave, okay, triangular wave, but it is have a 0 average, right. So, that means this axis is my capacitor current axis, right. So, this axis. Now, if we take the derivative, so here you will get a positive one, here negative one, here like this, and this is due to this term. There is a kind of a step, but Vc, if you take the derivative of the Vc, it is the capacitor current. So, it will have a triangular part, that means IC into C, C divided C dt equal to IC. But the main problem will be this due to this one, because if you take a double derivative of this, that means if you take another derivative of this, there will be a spike. So, your output voltage will have a huge spike here, and these spikes will be damped out soon because the inductance is small, but these spikes will come due to this term. And if you take a direct derivative, these spikes will go inside your controller and you need to attenuate, and that is why you talk about practical PID controller, where we take Kd into S divided by tau d S plus 1. and if you take tau d somewhat not very close, but somewhat close, that means you are trying to attenuate this filter, and this attenuation also have a penalty, because you are actually not taking a derivative action, you are slowing down. So, this was reported that this was shown in this paper with the experimental results. So, if you take the actual derivative, there can be real jump in the output voltage. Though we can reduce this effect by proper layout, but we still it is difficult to totally reject this effect. Now, the limitation of take a boost converter, the situation even is dangerous, because if you draw the, suppose if you draw the I will first draw the capacitor current diagram rather than inductor current. So, in a boost converter, the capacitor current will have a negative current, then it will have like this kind of current. So, this is my capacitor current. So, during this particular duration, this capacitor current is IL minus I0, and during this duration your capacitor current is simply minus I0. So, there is a discontinuity due to the inductor current, because it is getting connected during the off time and it is getting disconnected during the on time. So, that make the capacitor current discontinuous for a boost converter, and as a result, if you take again the derivative, because we have already discussed. So, what was our output voltage expression? Our output voltage, if we take this to be Vc and this to be VLC, then V0 is equal to Vc plus IC into RC plus, if this is my LC, LC into D 2 IC, sorry, dt, right. That means, since my capacitor current is already discontinuous, so this actually this is already a trouble, because if you differentiate at this point of discontinuity, you will get a huge spike. If you add a further derivative, then you will get a double derivative. So, you will get a double action, it will be problematic here. So, is a in a kind of impulse kind of effect you will get, and here the derivative of the impulse. So, it is it can inject a huge kind of spike. That is why you need to select the PID controller for a boost converter very carefully, otherwise it can be a disaster, like your controller error amplifier will simply get saturated because of the spike. Okay. So, that means generally that is why the PID controller straight away is very difficult to realize, but we will see that in a subsequent lecture. Even if we take a practical PID controller with a band limited action, you still can, because what we are going to do, if we link this PID controller with a switching surface, then we can tune this PID controller using the switching surface point of view, not from the small signal model, and then we can take back the pure band limited derivative action. So, alternative way, what we did, that we keep the proportional integral same, but we know the derivative, which was the Kd into dV0 dt, and what is because the derivative, sorry, we have taken what was the derivative action, we have taken derivative part, because our error voltage is this. So, this is our error voltage, right, error voltage. So, we took Kd dVe dt, that means we have taken Kd into ddt of Vref minus V0, and it is simply minus Kd into dV0 dt. And if there is no ESR, in ideal case, this dV0 dt is nothing but IC by C, but in practical case we have ESL effect and other effect. So, now if we take the capacitor information rather than direct derivative, so it will give something like a ideal derivative action, as if even though the circuit will have ESR, the circuit will have ESL, but by incorporating capacitor information, we can actually try to retain the ideal derivative action even for a practical circuit. So, that means we can resemble the ideal derivative action in a practical circuit by sensing either capacitor current or sensing load minus inductor minus load current, or their combination along with the estimation. So, that is possible. So, that means, but if you take a boost converter, as I said, the boost converter capacitor current during the positive cycle, it is nothing but minus load current, and during off phase it is IL minus I0. So, we can normalize, that means we want virtually like a capacitor current. That means, if I draw the boost converter capacitor current, we know the capacitor current is simply like this, but for a buck converter what we achieved was something like this. For a buck converter it was like this, right, it was like this, that was for a buck converter, right. But boost converter, this discontinuous jump create a real trouble for direct derivative, right. So, now why can't we emulate something similar for a boost converter, and that is exactly what we are doing, IL minus normalize, because in a buck converter our capacitor current is nothing but IL minus I0, because your average inductor current is same as average load current. But in a boost converter your I0 IL average is nothing but I0 by 1 minus D, and what is 1 minus D? It is your output voltage by input voltage into load current, that is my IL average. Okay. So, suppose if we create a virtual capacitor current by means of inductor current minus the normalized load current. What is the normalized load current? So, this is my normalized load current. So, I am normalizing the load current such that the average value is equal to the average inductor current. So, that their average at steady state will be 0, because under steady state their average. So, it is like a sense of capacitor, but not exactly the capacitor current for a boost converter, but it acts like a virtual capacitor current, which we are trying to create such profile even for a boost converter, which is something similar to a buck converter. And if we do that, this will look something similar to like a derivative action. So, for a boost converter, this normalized factor is nothing but IN is equal to, so you can take Kn into I0, where Kn is equal to 1 for buck converter and it is equal to V0 by V in at steady state for a boost converter. So, we are doing some normalization here, and that is the new formulation of PID controller. And if we do that, we are trying to get how can we relate whether. So, but one thing we should remember, the integral control that we are considering here, it has a very slow dynamics. And this only affects near steady state, provided that the recovery during large signal transient is much faster than the accumulation of the integral action. But if the integral action accumulation process, the speed of accumulation is comparable with the large signal time, the duration, then this will have a very high influence. But we are generally considering the integral slower, and we are talking about the time optimal control, where the recovery is extremely fast, where this actions comes near close to steady state. So, even though you keep this integral action, and if we do not consider this during the actual formulation, and if we incorporate in your actual implementation, they will not make much difference. but rather this will make your error nearly 0, so that your output voltage will be regulated at the desired value. So, now we want to visualize for a boost converter. So, these are the, you can see these are the trajectory, these are the on state trajectory. So, on state trajectories, see blue line, and if we take the green one, that means if I take this kind of waveform. So, there are family of this curve, these are my off state trajectory. Okay. Now, let us start, this is my starting point, this is my initial point. So, this is my initial condition, this is my starting point, initial point, and what I want, suppose it can be a starting point or it can be any arbitrary point, I want to reach to steady state, that means steady state means there will be switching, of course, because if you want to get a boosting operation, you need to turn on and off, you cannot operate the converter any particular switch configuration continuously, right. So, this is something like our desired behavior, that means we start from this point, you see, we start from this point, and this is my on state trajectory, it follow this path. Then suppose there is a switching surface which is a first order surface, it hit here and then it turns off and goes like this, and here it reaches steady state, that means this is a steady state action. Okay. So, if we remove all, then this can be related, that means is starting point in the time domain, inductor current like this, and then it come back to steady state. So, our this particular one is nothing but our current ripple, this is this current ripple, and you see any arbitrary point it start, it reaches there in one switching action. So, this is the fastest transient response and it reaches steady state immediately, and this is the switching surface where the gain is minus Kp, and I will tell you how we are going to relate it. So, some gain is there, and we have discussed this in the context of sliding mode control, and we saw that, or the boundary control, the previous lecture, I think in lecture number 47, we have discussed this. The selection of slope can play a role in shaping the transient, whether we want overdamp, perfectly optimal, or some more overshoot, that will be decided by the selection of this gain. But if we can do that, then we will get something like this action. Next, to reach steady state from any arbitrary initial point, okay, can we achieve this in one switching action, because that is what is my time optimal recovery or the fastest recovery. Then linear switching surface, can you do that, because here we are showing a linear switching surface, but we could achieve in one switching action. Then how to find the optimal slope, or rather I will say, if I take a different slope, what could be my behavior. Now, if I increase this slope, so earlier this was the slope, I increase the slope, then what will be my time domain behavior. So, because of the increasing slope, there will be more current overshoot, right, and you can see voltage overshoot undershoot also increase, because this side is my output voltage and this is my desired ripple, this is my ripple voltage, but I am going even either side of the ripple, that means there will be overshoot undershoot in the output voltage also. That means, if we increase the slope from here to here, we are getting more overshoot undershoot, which is not desirable. Similarly, if you reduce the gain, then you will get kind of a overdamp response, and that I am going to show using experimental result. So, that means we need to find the optimal slope, that means higher slope, more current overshoot undershoot. In fact, if you choose this slope, suppose if you by mistake, if you take the slope by mistake, if you take the slope like this, then it will be unstable, because the slope is higher than the slope of the on state trajectory, magnitude of the slope. As a result, suppose if this is your switching surface, that means you are actually reversing the switching logic, and this, that means this side trajectory, this side it is, if I take this trajectory here, it is going away from here, right. this is the on state trajectory, and this side also trajectory is going away. That means, this is a scenario where we are given a rejective region. That means, if you further increase the slope and if you make the slope even higher than the magnitude of this, you can see this is my on state trajectory, right. So, my on state trajectory, it looks like it is deviating from here. I am sorry, it should be the other way around, because we are increasing the slope. So, that means, if I take the slope like this, yeah, because this side my on state trajectory, if on state trajectory is going away from it, and this side if you see my off state trajectory is going away. That means, either side the trajectories are going away. So, this will lead to our rejective region, and that is not desirable, that will lead to. So, that means, very high large signal unstable, and it will simply saturate the inductor, because the switch will remain on continuously and it will saturate the inductor core and the voltage will collapse. So, we must select the slope accordingly. That means, this slope should be smaller. You can take smaller slope, it will be overdamped, but for larger slope you have to be very careful, particularly for a boost converter, because you may land up into a rejective region where the system will completely collapse and your inductor will saturate, it will damage the device and voltage will collapse. So, how can you link with this switching surface with your control logic? So, this is a first order switching surface where Kc is the current loop gain, is my average current, and this is exactly what I told, it is my normalized current. That is nothing but a normalization factor into load current, and this is my inductor current, this is my reference voltage, and this is my output voltage. And if we normalize, that means, if we make what is my Kp, it is my Kv by Kc. Normalize, then you will get this switching surface, and this switching surface, if you say IL is equal to this, because you have taken at point of switching, at the switching transition. That means, even if I write sigma, now we got sigma dot, this sigma dash, which is nothing but my I normalize minus IL plus Kp into Vref minus V0, and at transition it is 0, and this will lead to, if I take IL other side, it is Kp into error voltage. So, this is my error voltage plus our I normalized factor. So, this is my normalized factor, normalized load current. This is my inductor current, which I can realize, that means, this part I can realize using like a current mode control. This is simply my proportional gain multiplied by error voltage. So, if I write down again, that means, if you try to visualize, there are too many texts. So, first this is DOS, because we have divided sigma dash is nothing but sigma by Kc. Then we will get this equation, right, and we know that IL average, that capital, you can think of it is my normalized load current. Okay. And if at the switching transition it is 0, that means, this whole part is nothing but this part, and which looks a proportional gain, this proportional gain into error voltage, this is my error voltage. So, this is my error voltage into proportional gain, and that is added with the normalized load current, which is my IN, and the whole thing is subtracted from IL, because at the transition it is a comparator, and that can be linked if I want to use a PWM modulator, or we can use many other type modulator, and that we are going to discuss in the subsequent lecture. So, this modulator I have used here a pulse width modulator, but you can also use constant on time hysteresis modulator, hysteresis control technique, but the logic is this, up to this part is vital. So, this is a normalized load current feed forward, where this normalization factor acts something similar like a derivative action, and this is like a proportional control, Okay. So, this is a normally load current feed forward, where this proportional gain is nothing but the slope of this surface, and that plays a key role in shaping the large signal recovery. That means, if you want to achieve time optimal recovery, it is the proportional gain we have to select properly to achieve that, to find the optimal value of Kp. Now, if we take a experimental case study where this is the output voltage and you can see 1 volt. So, 1, 2, so it is a 5 volt output, 5 volt output, and input is where the input is 3.3 volt input. Here we take a smaller Kp because I am just playing, but we will formulate for buck converter with more elaborately, and we will give an expression for boost in the subsequent lecture. But what we did by this formulation, if we take a smaller value of Kp, you can see it is not the optimal recovery because there are few more switching number. But if we set the Kp, if we increase in a proper value, it is more or less optimal because you see there is a slight overshoot undershoot in the current, but this is close because we are talking about, and this mismatch is coming because we have a PWM modulator where the PWM modulator itself has a constant. So, we cannot achieve perfect time optimal, we will get rather proximate time optimal because of the modulator will put a constant in the on off time, right. If you further increase the gain, then you will see the overshoot will increase significantly, and that we have discussed in the phase plane. If you increase the proportional gain, you will get more overshoot undershoot, and if you further increase, it may so happen the whole system will collapse. So, you have to be very careful, and this will even lead to much higher current undershoot because it is a 2 ampere per division. So, much higher current undershoot, overshoot peak current. So, this may be close to optimal, this is like close to time optimal response, and this is even higher value, it is less, and this is like a overdamp response. So, the tuning objective is that we need to identify optimal proportional gain, and we also need to identify integral gain, because you see there is a small steady state error and this division is 1 volt. So, we are getting a steady state error of around 0.2 volt because we have simply considered a proportional control, there is no integral control yet. But I will show in subsequent lecture this integral control has no role, almost negligible role in the transient shaping, but it will eliminate the steady state error. So, we can use the integral gain tuning using our earlier small signal based approach, we can put some number, but we have to be very careful about this proportional gain and the derivative gain, which because it is coming from the current loop, because we have chosen IL minus IN. So, there is no gain because it is normalized, because if you go back to our original problem, if is, so since it is a first order switching surface, so we will have only one unknown parameter, only one, and that is exactly one, only one unknown, and that is nothing but Kp. So, we do not need to take, derivative gain is already taken care, only one, but only thing, since we are incorporating an integral action like a PID controller, which we have discussed even before that. So, this integral gain, since its action will be much more slower, so we will choose integral gain based on the small signal derivation, that is fine, and we will only try to eliminate the steady state error. Okay. So, that means our ultimate tuning objective is to find this optimal gain, and that we have discussed. So, in summary, traditional PID controller in DC-DC converter and their limitation we have discussed, and we saw that direct derivative will cause, it can introduce significant noise and we have to be very careful, but the alternative PID controller was useful, and that can take the structure of a current mode control with load current feed forward, where our ultimate objective is to get the right gain of the proportional controller. But if we do not want to sense load current, we can even go for voltage mode control as well, or even because current mode control is a quite common. So, then we can use an estimated load current if you do not want to sense load current, but the current sensing is required particularly for boost converter, where otherwise if you choose a higher gain, it may lead to complete collapse because of the rejective region. So, you have to be very careful, and we should use generally current mode control for boost converter. So, and we saw that current error, inductor minus load current, that gives something like a derivative action which is inherently there, and that is why we can think of a current mode control with a PI controller which will look something similar to a PID controller, the whole overall system. We have linked the PID controller with switching surface in switch mode power converter, and in the subsequent lecture we will show that we can use different type of modulator as well as different we have applied even for buck boost as well as buck boost to get similar optimal response, and we have set the tuning objective, and we have linked that performance optimization criteria where the choice of proportional gain seems to be the key factor. So, in the next lecture we are going to derive analytically what should be the right choice of proportional gain, and that will derive using large signal model where we can achieve time optimal recovery, and which was not possible in linear control or small signal model. So, with this I will finish it here. Thank you very much.